Hello everyone, today we are going to discuss with you about the oscillations, the rhythm of nature decoding oscillations. From the beating heart to the planetary orbit, an analytical descent in the physics of repetitive motion. Distinguishing repetition from oscillation. What is the difference between the periodic motion and oscillatory motion? Actually, motion that repeats itself at regular intervals. Suppose this is an insect, right? Insect is rising up and again it falls down, again it goes up, again it falls down. So this type of motion is known as periodic motion, right? Or this type of motion is also known as periodic motion. You see, this type of motion is periodic motion. A bouncing ball like this, these are all periodic motions, right? Oscillatory motions, a specific subset where a body moves to and fro about a fixed mean position called equilibrium. This is known as oscillatory motion. Every oscillatory motion is periodic, but not every periodic motion is oscillatory, like as example of circular motion. So this is the representation of periodic motion and this is the representation of oscillatory motion. The metronome of physics, period and frequency. Period, the smallest interval of time after which motion repeats. SI unit is second. Frequency, the number of repetitions per unit time. SI unit is hertz, nu is equal to 1 by T. The scale of oscillatory time. Micro scale, human scale, macro scale, cosmic scale. Micro scale, that means it is measured in microseconds. Human scale, that is measured in 0.8 seconds or 1.25 hertz cycle per second. Macro scale, it is 88 earth days. This is the scale of oscillatory time. And a cosmic scale, 76 years. So the frequency of oscillatory time can be measured in these four scales: micro scale, human scale, macro scale and cosmic scale. Displacement is a function of time. In oscillatory theory, displacement is the change of any physical property over time, not just distance. Mathematical representation is a function of time is equal to A cos omega t. Variables can represent position as x, theta as angle theta, and voltage V or pressure. These are variables of position. It can be angle in case of pendulum, right? And position in case of a spring, right? All these things are variables. So position variables can be present position or angle theta or voltage or maybe pressure. These are the variables, that is displacement variables. Defining simple harmonic motion or SHM. SHM is the simplest form of oscillatory motion where displacement is a sinusoidal function of time. Xt is equal to A cos omega t plus phi. This is displacement at time t, amplitude, max displacement, phase, state of motion, phase constant, initial phase at t is equal to 0. So in this way you can represent this, that is last step it will be t by 4, it will be t by 2, it will be t, and this is the function or of simple harmonic motion, right? Now we'll go to the next thing, that is this one, the geometric connection uniform circular motion. SHM can be visualized as the projection shadow of uniform circular motion onto a diameter. Here you see that this one is simple harmonic motion. Vector illustration, vector conial. As particle P moves in a circle, its projection P dash, projection P dash executes simple harmonic motion, or xt is equal to A cos omega t plus phi. Precise 2D geometric diagram. Velocity of oscillation. The derivation. The velocity is the rate of change of displacement. So Vt is equal to minus omega A sin omega t plus phi. Maximum amplitude is omega A. At equilibrium x equal to 0. Minimum magnitude, that x equal to 0. At extreme x equal to plus minus A. Negative sign indicates direction opposes positive x axis during half the cycle. This is the reference circle. The next one, acceleration and the restoring nature. Math. The acceleration is the rate of change of velocity. The acceleration is the rate of change of velocity. At is equal to minus omega square A cos omega t plus phi. or A t is equal to minus omega square x, x t is equal to that value. Inside, acceleration is proportional to displacement but directed opposite to it towards the center. So this is the reference cycle. This acceleration can be represented as minus omega square a cos omega t plus phi or equal to minus omega square x. This representing the acceleration of simple harmonic motion. This one phase relationship, the dance of variables. This is displacement. You see here, displacement can represent t by 4, here it is t by 2, it is 3t by 4, and it is t, right? This is displacement. Velocity can be represented in this way, it is t by 4, it is t by 2, it is 3t by 4, this is t, right? X is 0, v is maximum. So, in this way you can find the graph of displacement, velocity and acceleration in this way, that minus omega square a at t by 4 at this position, at t by 2 at this position, 3 by t 4 this is the graph of acceleration. In this way you can find the various relationship between the displacement, velocity and acceleration. This is the graph of simple harmonic motion of displacement, velocity and acceleration. The fourth law or Hooke's legacy. Newton's second law is F equal to ma. Substitute acceleration a equal to minus omega square x. Result F equal to minus m omega square into x. Define force constant k equal to m omega square. Final force law F equal to minus kx. Linear harmonic oscillator, a system where the restoring force is linearly proportional to the displacement. Force constant k, Newton per meter. Angular frequency omega root over k by m. System in action, the spring block oscillator. This is the equilibrium position, this is the restoring force, and this is expansion when x is greater than 0, this is less than 0 when it is compression. The period formula for a spring block system is t equal to 2 pi root over m by k. Heavy mass, high m oscillate slower. A step spring k oscillate faster. A step spring high k oscillate faster. The energy of oscillation. So kinetic energy can be defined in this way: k equal to half m v square half k a square sin square omega t plus phi. Maximum at mean position, 0 at extreme. So the kinetic energy is maximum at the mean position, 0 at the extreme. Potential energy equal to half k x square, half k x square is a square cos square omega t plus phi. Maximum at extreme. So the potential energy is maximum at extreme and 0 at mean position. Conservation of mechanical energy. In a frictionless system, the sum of kinetic and potential energy is constant. Here you see that this is the kinetic energy, right? And this is the potential energy. If you add this gives the total energy. This straight line is the total energy. So total energy is kinetic energy plus potential energy. It is equal to half k a square. This is the total energy, half k a square. Case study is a simple pendulum. Here see, this is the pendulum. It can be represented in this way. Suppose this is angle theta, right? This is L. The weight is mg, and this weight mg can be changed into mg cos theta in this direction, mg sin theta in this is the restoring force. Restoring force tau is equal to a minus L mg theta. Minus L mg theta using a small angle approximation, sin theta is equal to theta. So the period formula is equal to 2 pi root over L by g. Inside, the period is independent of the mass of the bob. Summary and key formula. Simple harmonic motion x t equal to a cos omega t plus phi. Force law F equal to minus kx where k equal to m omega square. Angular frequency spring omega equal to root over k by m. Pendulum omega equal to root over g by L. Velocity and acceleration V max equal to omega a equal to minus omega square into x. Total energy equal to half k a square, that is constant. Time period spring, for spring time period is 2 pi root over m by k. For pendulum t equal to 2 pi root over L by g. Thank you everybody for watching this video.